Hello everyone. In this video, we are going to discuss about this topic energy stored in a capacitor of class 12 physics from the chapter 2 electrostatic potential and capacitance. So here, initially, I am considering two uncharged conductors 1 and 2. Okay, now imagine that we are transferring a charge plus from conductor 2 to conductor 1. Okay, that is bit by bit. So at the end, conductor 1 gets, okay, that is we are transferring positive charge from conductor 2 to conductor 1 bit by bit. So at the end, conductor 1 will get some positive charges, and by charge conservation, conductor 2 will have some negative charges at the end. So you see, conductor 1, it is at a higher potential than conductor 2. So in transferring a positive charge from conductor 2 to conductor 1, some work will be done externally. So work done in moving a charge from one plate to the other, it gets stored in the form of potential energy of the system. So you see, we have this expression of potential V is equal to work done per unit charge. That is, we can write V is equal to W by Q. Okay, from this expression you can write work done as V into Q. Okay, now you see, if we consider a very small charge dq which is moving from one plate of the capacitor to the other plate of the capacitor. So work done in moving a charge dq from one plate to the another can be written as dw, a small amount of work done. That will be equal to what? Potential V into dq. Okay, now you see this can be written as what? dw is equal to, we have C is equal to Q by V, capital letter Q or small letter q, which one you are using that you can use. Okay, I'm just using small letter q here, so Q by V. So from this expression you can write V is equal to Q by C. Okay, so I'm here replacing this V with Q by C. So we can write dw is equal to Q by C into dq. So you see, this dw is equal to Q by C into dq. This is actually the work done in moving a charge dq from one plate of the capacitor to the another plate of the capacitor. So you see, initially there were no charges in the capacitor plate, and we are charging the capacitor from 0 charge to an amount capital letter Q amount of charge. So the total work done for that will be equal to what? Integral 0 to Q dw. That is, we want to integrate this small amount of work done to get the total work done. So this can be written as integral 0 to Q, because we are charging the capacitor from 0 to Q. Then what is dw? Q by C into dq. Okay, this is equal to, see here the integration variable is Q charge. So you can take this 1 by C outside. So 1 by C into integral 0 to Q, Q into dq. Okay, now you see this can be written as W is equal to 1 by C into, what is integral 0 to Q, Q dq? We have this expression, no? Integral x raised to n dx is equal to x raised to n plus 1 divided by n plus 1. So by using this expression, you can write integral q dq is equal to, see here in the place of x we have q, in the place of n we have 1, because q raised to 1 is q. So this can be written as q raised to 1 plus 1 divided by 1 plus 1, which is equal to what? Q raised to 2 divided by 2. Okay, so here you can write W, the total work done, W is equal to 1 by C into integral 0 to Q, Q dq is Q square by 2 within the limit 0 to Q. So we have to apply the limits. So this becomes what? I am taking 2 here and I am writing it here. So 1 by 2C into Q square within the limit 0 to Q. Now we want to apply the limits. So when we apply the limits, we can write it as W is equal to 1 by 2Z into, okay, first you apply the upper limit, that is capital letter Q. So Q square minus lower limit, that is 0, 0 square. Okay, so this can be written as what? 1 by 2c into q square minus 0 square is q square. That is, you can write the total work done W as q square by 2c. See, since electrostatic force is conservative, this work is, that is W is equal to Q square by 2C, this work is stored in the form of potential energy of the system. So we can write this W as U here, so that U is the potential energy of the system. U is equal to Q square divided by 2C. Okay, now you see, let us get some other expressions for this U in terms of C, V, etc. See, we have this expression, no, that is Q is equal to C into V. Okay, so when you substitute this Q as CV, what happens to this expression? This becomes U is equal to Q square by 2C. So Q is replaced with CV. So Q square means CV the whole square, which is C square V square divided by 2C. 1C from the numerator, 1C from the denominator cancel, so that you will be getting 1 by 2 CV square. So this is another expression for the potential energy in terms of C and V. Okay. Now, see, if you consider the same expression, U is equal to Q square by 2C, here we replaced this Q with CV. Now, let us replace the C. See, from Q is equal to CV, you can write C is equal to Q by V. So, replace the C with this expression Q by V. So, what does it become? U is equal to Q square by 2C. That is 2 into Q divided by V. Multiplication with reciprocal. So Q square into V by 2Q. Okay, 1Q cancel. So that you will be getting the potential energy as U is equal to half Q into V. So this is also another expression for the potential energy stored in the system of, the capacitor. Now you see, for a parallel plate capacitor, we have the expression for the capacitance as C is equal to epsilon 0 A divided by D, where C is the capacitance of the capacitor, A is the area of each plate of the capacitor, and the small letter D, which is the distance of separation between the two plates of the capacitor. Okay, see, we have the expression for the energy stored in a capacitor as U is equal to Q square by 2C. Okay, now what I am going to do is I am going to substitute this C as epsilon 0 A by D. So that this becomes Q square divided by 2 into epsilon 0 A by D. Okay, now see, multiplication with reciprocal will give you Q square into D divided by 2 epsilon 0 A. Okay, now what I am doing is, see, we have this expression now, surface charge density sigma is equal to charge per unit area. Okay, so from this you can write sigma into A is equal to Q. So what I am going to do is I am going to substitute this Q as sigma A. So that it becomes what? We can write it as, this is equal to, Q can be replaced with sigma A. So sigma square A square, Q square, no, sigma square A square D divided by 2 epsilon 0 A. Okay, so we are getting another expression for the potential energy stored as sigma square A square D divided by 2 epsilon 0 A. So this is another expression for the energy stored in a capacitor in the place of a parallel plate capacitor. Now you see, the surface charge density sigma, it is related to the electric field E between the two plates of the capacitor by this expression E is equal to sigma by epsilon 0, which we have already discussed in our previous video. So from this expression you can write sigma is equal to E into epsilon 0. So now what I am going to do is I am going to substitute the sigma as epsilon 0 into E or E into epsilon 0 as to this equation. Okay, so that this equation becomes U is equal to sigma square, that is E square epsilon 0 square, okay, A square D divided by 2 epsilon 0 into A. Okay, so you see 1A cancelled, 1 epsilon 0 cancelled, so that you will get it as 1 by 2 E square epsilon 0 then A into D. Okay, so this can also be written as what? U is equal to half epsilon 0 E square into A into D. Now, if I take this A into D to this side of the equation, it becomes what? We can write U divided by AD is equal to half epsilon 0 E square. See, this is like area into, the distance between the two plates of the capacitor. That product is actually a kind of volume. So this is like energy stored per unit volume of space, which is actually known as energy density of the electric field, and which is represented with this letter U dash. That is, U by AD can be replaced with U dash. So that energy density is equal to half epsilon 0 E square. Okay, so you see, though it is derived for a parallel plate capacitor, it holds good for electric field due to any configuration of charges. So in this video, we have discussed about energy stored in a capacitor. I hope it is clear to you. Thank you.